we are finally ready to state Green's theorem. We won't prove Green's theorem. You can see the textbook for proof of a special case version of Green's theorem. Actually, there's two different versions of Green's theorem. So let me show you the more commonly known version of Green's theorem first. It's the circulation curl version of Green's theorem. So let C be a piecewise smooth, simple closed curve enclosing a region R in the plane. Let F, written as mi hat plus nj hat, be a vector field, Mn having continuous partial derivatives, an open region containing R. The counterclockwise circulation F around C equals the double integral. This is the curl. This is the curl of F over R. So this right here is the circulation, and this is the double integral of the curl. Let me just remind you of all of this here. This definition here from section 16.2, flow is called circulation if we're integrating around a closed loop here. And so that's just f dot dr for the integral of f dot dr around a closed loop is called circulation. So this right here, these two sides are both circulation. And then the right expression here, this expression partial m partial x minus partial m partial y is the k component of the curl, as we saw earlier in this section here. So Green's theorem says that these two things are equal to each other. It is, let me just draw a picture here. So we have some curve C here. And then we have some region R. The circulation, the integral over C of f dot dr is equal to the double integral over R of curl f dot k hat dA. The circulation around the boundary of this region oriented counterclockwise. We should always be orienting our curves counterclockwise. The circulation around the boundary here is equal to the double integral of the curl over the inside region here. So let's just, before we do anything else here, let's interpret circulation curl Green's theorem in the case of water rotation in this form. F is negative yi hat plus xj hat. So this looks something like, let's see here. Okay, so this is a rough sketch of what this vector field would be looking like. So, so then we also want to drop our curve C here, and we'll do unit circle. So what the right side of this is saying here is having to do with how much flow. So the integral of m dx plus n dy is equal to the circulation around the boundary here, around the unit circle. If you crunch it out, you get 2 pi. How much water is flowing around the circle? It's 2 pi. But then the other side here, the curl integral, the double integral over R of partial n partial x minus partial m partial y dA. This is the integral of curl here, and this is also equal to 2 pi. Remember, my interpretation here of curl is how much is it turning your How much is it turning your paddle wheel? You drop in the paddle wheel in here. How much is it turning it? If we're integrating that over this entire region here, we're seeing we get 2 pi. These two answers equal. I mean, that's a consequence of Green's theorem. These two expressions need to equal here. I'm sweeping the computational details under the rug. It's easy to verify it for yourself. And we certainly will verify Green's theorem in other similar cases in future videos here. But let's just appreciate that the equality here of circulation equaling curl makes sense. If you're having circulation around the boundary, that should mean that you're rotating counterclockwise, and counterclockwise rotation means that your k component of your curl is positive here, so it makes sense that there's a connection between these two. And so Green's theorem, accordingly, shouldn't be too surprising. Okay, so this is the circulation curl version of Green's theorem. We will definitely apply, verify this in future videos, apply this. Let's wrap up this video. Next video, we'll see the other form of Green's theorem.